Let's look at one more example of using the dot product. This one is from physics, so if you don't know much about physics, I apologize in advance, but we're going to have a look at this anyway. So in physics, if you have a constant force F, and remember force is a vector, right? So that's why I have this in boldface. If we have a constant force that is exerted on an object as it moves through a displacement d, and remember displacement is also a vector, then the work done by the force is the distance traveled times the component of the force in the direction of travel, right? So we have this set up here. We have an object that moved from this starting point to this ending point, so along the displacement vector v. As it's moving, it is experiencing this force capital F. It's a little misleading to have both of these vectors drawn in the same diagram because they have different units, but still, we're gonna do it anyway. And so this force, right, there's some portion of this force that points in the direction of travel, and we want the distance that we traveled times the length of, times the part of this force pointing in that direction. Okay, so the distance traveled, well, if d is our displacement, the distance traveled is actually just the magnitude of d, right? And the component of the force in the direction of travel, well, that is the component of the in the direction d of the force F, right? So the work is the magnitude of d times the component in the direction of d of F. All right, but we have a formula for this scalar component of F in the direction d. So let's write out what that is. It is, I missed my vector hat over here. So this scalar component of F in the direction of d, that is, let's see, it was d dot F divided by the magnitude of d. So these magnitudes cancel, and it turns out the work is just the displacement dotted with the force. Right? So this is really convenient. The dot product actually encodes exactly what we need to compute this work. Notice that the displacement vector is in fact a vector. Force is also a vector, but work itself is a scalar. Right? The dot product takes two vectors but produces a scalar. So this work quantity is a scalar. While we're at it, let's look at units. So the units for force are newtons. The units for displacement are distance units. And if we're using newtons, right, a newton is what, like a meter kilogram per second squared. If we're using meters, then we had better also measure our displacements in meters. So the units for this whole mess is meters times newtons, and that's meters squared kilogram by second squared. And this is what's called a joule. Right? So Newton times a meter is a joule. So this is the units for work, and this is also the units for energy. Right? So work is a measure of energy. All right, so the point of all of this is that work is given just by a dot product of two vectors, which is pretty convenient. Right, so for a constant force, if you have a constant force applied as an object moves through a displacement d, the work is just the dot product of the force and the displacement. All right, so for example, how much work is done by this force, 3, 1, minus 2 newtons, on an object that moves from the point 111 to the point 456. So we need to calculate the displacement vector first, right? Because these are points in space. These are not, neither of these are the displacement vector. So to find the displacement vector, right, we just need to do the end point minus the starting point. So that's 4, 5, 6 minus 1, 1, 1. So that's going to be, sorry, this is a vector now, so I'll use angle brackets. 3, 4, 5. So there's our displacement vector. So our work is, remember, work is force dot displacement, or displacement dot force, either way. Our force is 3, 1, minus 2. And our displacement is 3, 4, 5. And so 3 times 3 is 9, plus 4 times 1 is 4, minus 2 times 5 is 10. So let's see, 13 minus 10, 3. And this is in joules, right? These distances are in meters, so this displacement is in meters. So these, all of these displacements are in meters. The force is in newtons, and so at the end we get a newton times a meter, which is a joule.